Gonzalo Ortiz. I'm a staff software engineer in StarTree, and today I'm going to talk to you about how to improve query performance in multi-stage query engine in Apache Pinot. As you may know, Apache Pinot is a database focused on real-time analytics, and initially we had a single-stage query engine, which is our initial query engine, which is a simple one, and it's focused mainly on running very fast analytic queries. But there are some parts of the SQL standard that we cannot implement in single-stage query engine. One of them is the join expression, which is difficult to evaluate when you are dealing with the large size of data we are using in StarTree Pinot, right? So this is why we created the multi-stage query engine, which tries to solve all these issues we had or limitations we have in single-stage query engine. Both engines can still be used, but multi-stage query engine is a little bit more complex, and at the same time gives you the ability to write more complex queries, right? In single-stage query engine, when you want to improve the performance, you usually focus on reducing the number of rows you are reading from disk. And you can do that by different techniques like table partitioning, single column indexes, or StarTree indexes, which are being used to improve the performance of some aggregates. Okay, in multi-stage query engine is more or less the same, but there is an extra layer of complexity because rows are read from disk in the same way they are read in single-stage query engine, but they are also shuffled between different servers, right? And this is another thing we have to reduce. You can apply the same techniques you are applying in single-stage query engine, but there are some new ones that I'm gonna introduce you. First of all, we need to understand where are our bottlenecks, right? Because that's the first thing you need. When you want to improve your query, you need to understand that, especially multi-stage queries can be very large, and you don't want to be focused everywhere. You want to be effective and focus on places where the operators where time is being consumed, right? In order to do that, we provide two different tools. One of them is the explain plan. The explain plan is a tool you can use before your query is executed, and when you ask Pinot to use this tool, the thing it does is to optimize the query in the broker and returns the plan, which shows you the shape of your query, the things the query is going to do. And in Pinot 1.0, which was released in September 2023, this plan was focused on the logical plan, which is, again, the things that the broker can understand from the query. And this specifically does not include things like indexes or segments made prune, things like that. In Pinot 1.3, released in February this year, we added a new mode you can enable where the broker actually asks servers about all that information, indexes being used and that kind of things, in order to give you a better view of the explain plan, of the things that are going to be executed, right? The plan is pretty simple, similar, but it includes the information we didn't have before. And in order to enable this, in this version of Pinot, you need to enable it explicitly with a query option, and can also be tuned on by default if you change some configuration in Pinot. They are specified in the documentation, and probably in the next release of Pinot, this feature is going to be enabled by default because we think it's very useful. But even the explain plan is great. As I said, it's only static information, only information we can infer from the query before running the query. Query stats are just the other side of the coin, right? Query stats are collected whenever you run a multi-stage query, and these queries are enriched. The result, the payload we send you to the clients that are running the queries includes all that information, all these stats, right? This feature was introduced last year in Pinot 1.2, and the information is shown as a very large, for human scale at least, JSON, which includes several stats for each operator that has been executed in your query, right? This is very useful, but the main issue we found with that is that it's not very easy to read for humans. You can use some tools to analyze JSONs and draw that as a tree, and then you can analyze that. But we wanted to provide that, make the experience using Pinot easier and provide that by default in our system. This is why in Pinot 1.3 we introduced the new query stat visualizer. You can access that in the query UI. And here you have the same information. In fact, the thing it does is to read that JSON and just show the same information in a more beautiful way. And here you can see the same information, but draw as boxes connected with lines, which show how the information is moving from one node to the other, right? We still have some things to improve because there are still too many information. We would like to improve that, remove all the noise we have, all the stats that may not be so useful. We would also like to add some extra hints in the tree, saying, hey, maybe you need to add an index here, or maybe this join is not very well optimized. That's something we want to introduce in the future. Another thing we really think that is super important to add is including stats when query fail, because right now stats are always collected, but they are only sent when the query finishes. In cases, for example, when a query timeouts, it's very complex to understand which part of the query is the one that is taking so long, right? Because we don't include all these stats, and we don't have enough context to understand that. You can read that from the logs, but that's not very, very user-friendly. So these are things we want to improve in the following versions. Now that we know where the bottleneck is, or where they are, there are several techniques we can use. One of them is actually try to reduce the shuffling in the rows. And even shuffling can happen in different places. The most important one is on joins, because there is usually where more rows are moved from one server to the other, and also the place where we can apply more optimizations. First, I would like to tell you show you how to implement a very naive join. Let's imagine that you have a cluster with 3 servers, and each server server 1, 2, and 3. And there are 2 tables, A and B, and each square there, the red one and the blue ones, are different segments of table A and table B, respectively. The easiest way to implement a join is to say, okay, let's move all data to a single server, and then execute a normal join there in the same way Postgres or MySQL will do, right? You can do that, and it works. But the main issue we have here is that Pinot has been designed to support a very large amount of information, and that's one of the reasons why we actually have different servers, right? One of the reasons is because we want to have high availability, but the other one is because Pinot stores so much information that you most of the time cannot hold all the information in the same server. So this technique is not being used in Pinot because it can only be used in the most trivial cases, right? There are other techniques Pinot use. I'm gonna talk about 2 of them, but there are others, and I recommend you to go to the documentation to read about them. We explain them with the same style, the charts in the same style, and I think that is a very educated thing to understand how the database works under the hood. The main optimization we have, or the one that is used most of the times, is one that we can apply whenever we have an AKI join. And the idea here is that we have a select blah, 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 join another table on a.call2 equal b call3. Okay. In this case, again, think about the same scenario we had before, these 3 servers with these tables. In this case, the thing we do is to create some virtual partitions. These partitions are virtual entities, not something that actually exists in the segments. And the thing we do is to say, okay, given that they are being joined by equality, let's assign these partitions in such a way that we know that if 2 columns from A and B can be joined, they are going to be in the same partition. And the thing we actually do is to apply a hash, decide parallelism. In this case, for example, we choose a parallelism of 3, and say, okay, let's apply a hash in the value we are going to use to join, and then module the number of partitions we have in such a way that we are going to guarantee that all rows whose module 0, whatever hash module is equal 0, are going to be in this partition. The ones that are module 1, they are going to be in the other one, and module 2, they're going to be in the other one. Then the servers send rows to these partitions, these virtual runners that are being executed in the server actually. And obviously the servers that already have these rows don't need to move them, but the others need to be moved, right? In this mode, we can then apply the join locally for each partition because we know that they are going to be disjoint. And after that, we can just concatenate the results, and that's it, right? Here the number of rows that needs to be shuffled are the same than in the previous case, but here we can scale horizontally as much as we want because we can create as many partitions as we would like to have. Then that's cool, but that's using some virtual partition. That has nothing to do with the actual partitions you may have in your table. You may already have some partitions created at ingestion time, and if these two partitions are compatible with the kind of join you are executing, you can apply, Pinot can apply better optimizations. Let's say that, for example, you have a table that is partitioned by the user ID. Two tables, table A and B, are partitioned by user ID, and there you are, for whatever reason in your query, you are joining these two tables by that user ID. Then you know that if the joins, the two rows are going to be joined, they have the same user ID, and therefore they are in the same server, right? Let's imagine in this case, I modified these boxes a little bit because I added an extra number. The first number is the number of the physical partition, and the second number is the same ID we had before. Here we can see that in server 1, we don't have anything, we have no partition for table B, but in server 1, we have partition 1 for both A and B, and in server 3, we have partition 0 for both A and B. So Pinot automatically can detect that and say, hey, I can run this as a virtual partition and use the parallelism I want, but that will require to move some rows, right? Instead of doing that, the thing I can do is to say, hey, let's use the same number of partitions we already have at physical level, and then use the same servers as the ones that are going to execute that partition. So the thing we do is to say, okay, in this case, we only have two partitions, 1 and 0, and let's schedule partition 1 in server 2 and partition 0 in server 3. Then we don't need to move rows from one server to the other. They are going to be in the same server. And then we can execute, again, the same algorithm, concatenate the results, and that's it. We have the same result, but we have to move literally no rows from server to server, right? That's the ideal case, but cannot be applied everywhere because sometimes you want to partition by something, but join by another thing. Well, in that case, you have the other solution, okay? Cool, this is mostly about distribution. How can you improve your joins? Okay, but there are some advanced optimizations you can apply to your queries. One of them is pipeline breaker. Usually databases, and Pinot is not an exception, first receive the string you want to execute, optimize that, and then actually execute it, right? In pipeline breaker, we break that pipeline a little bit, and the thing we do is to apply that optimize plus execution phase more than once. The thing we do, for example, let's imagine that we have this query, and in this query we are gonna, instead of actually working with the string, let me draw some diagrams. I think it's gonna be easier to understand. And here we are scanning a large table and another table that may be smaller, joining them and then projecting some results. Okay? With the particularity that the only columns that we are projecting come from the large table. In this case, the thing we have to do is to actually read the whole table, both of them, in fact, then join them just to find out that we are removing, we don't need all the rows in the large table, only the ones that match the join condition, right? This is an inefficient because as I said, we are reading a lot of rows, so we are paying that cost in memory. Then in this join, we probably need to shuffle these rows, which means that we need to pay a cost in network, okay? This query is also equivalent to the older one. This is with a join, and this is with a filter. Why is equal? It's equivalent because, as I said, we are not projecting columns from the right-hand side, the table 2. We are only using tables from the other larger table, right? And even if this is not a join, it's anyway similar in terms of cost because, again, we still need to read everything. But this is where the pipeline breaker appears. And it says, hey, cool. Let's evaluate first the scan on table 2, right? And let's assume that this is going to return a list of literals, a list of rows that are in the table, right? Let's assume that this table is super small and only the values 1, 2, and 3 are returned, okay? Then let's optimize, instead of running the whole query, let's optimize the query now. And given that we know that this subquery actually is evaluated to 1, 2, and 3, let's substitute that. And then we have this query. In this query, we don't have any join. We don't have any subquery. This is a query that you could run in single-stage query engine. And in fact, if there is an index, for example, in the large table in column 2, we can use that index to implement this query and do something like this, where we are not reading all the tables all the rows from the table, but the thing we do instead is to use the index to only read the rows that actually fulfill the condition. This is orders of magnitude more efficient than the other plan, and it's equivalent. It's equivalent as long as some conditions are fulfilled. One of them is that this only works for either expressions written in the form where this column in the subquery, or in a more general case, in inner joins, where the column from the right-hand side are not projected, as I showed you before. And something I didn't tell you is that there are some particularities if the right-hand side has values that have been repeated. For example, in this query here, we have this, it's the same example as before, but the right-hand side is called tiny table. But Pinot doesn't know that that tiny table dot call3, which is what we are joining on, is unique. There may be several repetitions of some value. Let's say that instead of 1, 2, and 3, the value is 1, 2, 2, and 3. Then all columns, or rows, sorry, in table A, whose column 2 is equal to, are going to be projected not once, but twice in the query that we have in the left-hand side. Instead, if we write something like the thing we have in the right-hand side, where we have added this distinct key, we are telling Pinot, hey, please drop all repetitions, and then just use the unique values. When Pinot sees that, it can then transform this into an in expression, and therefore they can apply the pipeline breaker. So sometimes, even if this seems more complex to understand, and it looks like Pinot has to do more things, in fact, it may be faster than the other query. As I say, there are some limitations, right? We cannot project the columns in this case, the B table, and we need to be sure that this other column is unique. What's happened? I mean, we can apply this distinct and stuff, but sometimes we actually want to have repetitions, and sometimes we actually want to project columns in B, right? What can we do in these cases? In these cases, one trick we can apply is, again, this is the same query as before. I'm going to draw it as boxes. And the thing we can do is to, instead of executing this simple and easier to read query, the thing we're going to do is to introduce a new filter. This filter is exactly the same as we had before. This is a scanning table in tiny table. And the thing we're going to do is to introduce the same filter using the same join condition. If we do that, it looks like we are doing more job than necessary, right? Why are we adding this extra phase? But in fact, the thing we are doing here is to apply the same pipeline breaker we saw before. And therefore, this can be used to reduce the number of rows we read from large table. In order to do that, Pinot is not able to do this kind of optimization right now by itself. So we need to help him. And in order to do that, we need to write a more complex query, which is quite difficult to read, right? At least more difficult to read than the original one. This is why we want to introduce a new feature. This is not something we support right now, but something we are working on, which we call dynamic filterings. And the idea here is that you can write the original query, and Pinot itself is going to understand that this optimization can be applied, not in every condition, but in, for example, if you have indexes in these columns and blah, 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 and then apply the optimization for you. This optimization has, apart from the fact that it's more difficult to read the query, it has another problem. The problem here is that we are reading from this tiny table twice, right? If it's just a tiny table, that's not problematic. But if, for example, this query, this thing here is not just a scan, a table, but it's evaluating some expensive subquery, like, for example, grouping by something that cannot be optimized by a StarTree index, then this optimization may not be very useful. And in order to, like a first step before supporting dynamic filterings, we introduce it in Pinot 1.3. And this is the last trick I'm going to tell you today. We introduce spools. Spools are a tool we use to detect that some parts of your query have been repeated and then replace them. Let's say, we see this query, for example, where we have 2 joins and the same expression is being used in 2 of them, right? So the thing, Pinot can automatically detect that and say, hey, these 2 are equivalent. They are going to return the same rows and they are going to do the same thing. So let's remove one of the instances. And the thing I'm going to do is to send from the one that survives the information to both joins. Okay. By doing that, we only need to execute this query only once. And this means that we only need to read these rows only once. Even if we need to shuffle them in any way, we can reduce the amount of job we have to do, right? We even introduce this feature into the visualizer I showed you before. So whenever a spool is being used, you can see that, for example, in this case, this mailbox send is sending information to these both mailbox receives, which they are each one joined to attached to a different join, and they are representing the same query I showed you before. So this is something you can enable. It's disabled by default, and can be enabled. The documentation in the web page tell you which options you should turn on to be able to use that. And Pinot is going only to use this thing whenever it finds that two stages are similar. Okay, that's all for today. I just wanted to also add some chronology of the things we have been adding in the last year in multi-stage query engine, Pinot 1.0, Pinot 1.3, and any future work we want to be working on. The QR there is just a link to our Apache Pinot community Slack, where you can ask any question you have or propose new ideas, so we can have your feedback in the things we need to introduce or the better things we can improve. That's all. Thank you very much.
you.